Okay, good morning, both of you. We'll share the screen soon. Okay. Yeah, I hope you can see the screen. Okay. So we were looking at the example from queuing theory and recall that customers come as per homogeneous person process N and infinite number of servers. Nobody has to wait for service. And be defined by MT the number of customers who finish their service by time T. Yeah. So we wanted to show that, or rather we want to show that this MT is a non-homogeneous Poisson process. So one of the important things of this non-homogeneous Poisson process is at independent increments. So we want to show MT has independent increment property. We were in the middle of the proof, and for that we take, this should be T1. Just please correct it. I have corrected in the notes, but I have not corrected it here. So we define by M1 those who finish their services during the time interval T1 to T2, and M2 is T3 to T4. So these are disjoint intervals. So we want to show that these are independent, not only independent, they are Poisson random variables. Okay, so those who finish the service in the interval T1, T2, we call type 1, the other ones type 2, T2, T3 and T4, and M3 are the others who have arrived by time T4, but whose service, or they are not of type 1 or type 2. That means their service might not be over even by time 4, or they might have finished their service between the T3, T2 to T3, or even before T1. Okay. So these are non-negative integer valued random variables. So we want to show that M1 and M2 are independent. M3 is going to serve as a kind of to help us in solving. So we condition with respect to NT4, and then you can easily see that it is this. And we want to use that relation between order statistics and Poisson distribution, Poisson processes. So UIs. Yeah, these things we looked at. So we had seen that this conditional probability is given by this expression, where these PIs are probability that U1 is of type I for I equal to 1, 2. And of course, P1 plus P2 plus P3 is equal to 1. So this is where I think we had stopped. Okay. Now, yeah, so this is where we had stopped. We want to calculate this P1, P2, etc. So P1 by definition is the probability that any of the UIs are of type 1. Of course, these are all IAD uniform. So the same thing as probability of U1 is of type 1. Type 1 means what? The person's service is completed during T1 to T2. Of course, all these fellows have come between 0 and T4. So if the service is going to be completed during T1, T2, the possibilities are that that person arrived before T1 and the service is completed during T1, T2. Or the person came between T1 and T2 and the service is completed during T1, T2. So this probability of the first term, the arrival during 0 to T1 and service completed during this means since the time of arrival, let's say he arrives at time S, and S is a time point between 0 and T1. If he has arrived at time S, then if his service is completed before T1, that would correspond to the G of capital G. The service gets over before T1 minus S. But the service is completed only during this period. So therefore, this probability is same thing as, given that he has arrived at time S, the probability that the service time lies between T1 minus S and T2 minus S. So in other words, this first term, probability arrival during 0 to T1, service completed during T1, T2, to calculate that probability, we condition it with respect to U1 arrival. U1 is equal to S. That is, the customer has arrived at time S. And we know that this U1 has a uniform density over 0 to T4, because these are all, remember, UIs are uniformly distributed over 0 to T4. That is what that theorem 1 of yeah, this is dictated by our experience with using the theorem concerning the connection between Poisson processes and the order statistics of the uniform random variables over this interval. And of course, as usual, the UIs can be taken to be independent of NT, the process NT, as well as the service time random variables. The random variables which gives the service time for each customer. Yeah, so this is where. So this is, in this step, we are using that theorem. Yeah. So to compute the first probability, so the customer has arrived before T1, but his service completed during T1 to T2. So that is same thing as conditional on U1 equal to S, where S is a number between 0 and T1. Probability T1 minus S less than the service time, this thing, random variable, less than or equal to T2 minus S. And this is the probability density function of the uniform random variable and ds. Now, the second term, the arrival has taken place during T1, T2, service also completed during T1, T2. So if between T1 and T2, if he has arrived at time S, the amount of time taken for his service is less than T2 minus S. So by the same reasoning, we are getting this. Only thing is here it is integral T, the customer has arrived between T1 and T2. Here we are not using anything except conditioning that with respect to U1 and expressing these probabilities. Okay, please note it down. All right. Now, we also know that these UIs are independent of the service time random variables. Yeah, these random variables are independent of the service time random. Service time random variable, remember that they have the distribution function G. So because of the service time random variables and U1 are independent, that expression is equal to. So this can be dropped, and this we just write down this expression in terms of symbols. So this is G T2 minus S minus G T1 minus S. That's what we have to do. So the first integral is G at T2 minus S minus G at T1 minus S and 1 over T4 ds. And similarly, in this case, this guy probability is independent of this thing. So it is G of T2 minus S. So the G T2 minus S here, it is getting integrated with respect to this function from 0 to T1. And here it is getting integrated over T1 to T2. So combining this one, the second term, and the first part of this thing, we get 0 to T2, G at T2 minus S, 1 over T4 ds. And then what remains is just this one. So that is integral 0 to T1, G at T1 minus S, 1 over T4 ds. So now in this interval 0 to T2, you call this T2 minus S as R. Then you can see this same thing as, of course, 1 over T4 we have brought out. Integral 0 to T2 GR dr. And similarly in this integral, you put R equal to T1 minus S. So in this thing, so two simple changes of integrals are involved. One over the interval 0 to T2, another one over 0 to T1. So that is equal to 1 over T4 times integral T1 to T2 GR dr, where G is the distribution function of the service time. So we have got an expression for P sub 1. Okay. So P sub 2. P sub 2 is probability, U1 is of type 2. And repeat the same type of argument. Only thing is, in that case, it will be 0 to T3 and completed during T3, T4 and arrival during T3, T4 and completed over this. So that corresponds to these two terms. So 0, so the first thing is that the customer could have come any time between 0 to T3, but the service is completed only during that interval T3, T4. So therefore, given U1 equal to S is a number between 0 and T3, it is the probability the service time takes value between T3 minus S and T4 minus S. And similarly, the second term, the customer has arrived during T3, T4 and service completed also during T3, T4. and also use the service time random variables are independent of the UIs and so on, as we have done before. And then you will get now this expression. 1 over T4 integral from T3 to T4 GR dr. So in the earlier thing, it is this thing T1 to T2. Well, P3, we don't have to really do anything, because remember that we have already observed that P1 plus P2 plus P3 equal to 1. See, the entire discussion concerns MT, those whose service has been completed during 0 to T, or leaving the thing. So these are P3, the type 3 people could still have to wait beyond T4, or they might have finished their service before T1 or between T2, T3 and so on. So P3 is 1 minus P1 plus P2. Please note it. Okay. So we now collect these things together, go back to our earlier expression. Yeah. So probability, so we want to show M1 and M2 are independent Poisson random variable. So this is probability M1 equal to K1, M2 equal to K2. So that we had introduced that K3 can vary between 0 to infinity and so on. And then this given NT4 equal to this number, K1 plus K2 plus K3, multiplied with this. So now what we have done is we have got a handle on that expression. So this we had observed that this probability M1 equal to K1, M2 equal to K2, M3 equal to K3, given NT4 equal to K1 plus K2 plus K3 is, we have already found it is this. This is the trinomial things and so on. And these things had to be determined, and we have now found out these. So now we have to put all these things together. So the first step is to this expression. So that is what we had found. It was this times probability NT4 equal to K1 plus K2 plus K3. So this we know. This is precisely 1 divided by K1 plus K2 plus K3 factorial. So we know that NT4 has a Poisson distribution with parameter lambda times T4. So therefore, the probability NT4 equal to K1 plus K2 plus K3 is 1 over K1 plus K2 plus K3 factorial, lambda times T4 to the power this number, K1 plus K2 plus K3, times e to the power minus lambda T4. And these things we just, so this factorial and this thing will cancel out. And what remains, we group this thing. So there is P1 to the power K1 and lambda times T4 to the power K1. That, and then e to the power minus lambda T4. Lambda T4 we can write as lambda into 1 into T4, but 1 is equal to P1 plus P2 plus P3. So using those things, we can write it out as 1 over k factorial times lambda times P1 times T4 to the power K1 e to the power minus lambda times P1 T4, and similarly here and similarly here. Yes, this thing is something is missing here. This is e to the power minus lambda times P3 T4. Anyway, you have the expressions here. So these are nothing but the first one is the probability that the Poisson, a Poisson random variable with parameter lambda P1 T4 takes the value K1. So that is this term. The second term similarly is the probability that the Poisson random variable with parameter lambda P2 T4 takes the value K2. And similarly the third term. I'm sure you would have done calculations in your earlier courses, probability course, which involves Poisson random variable, Poisson distribution. Similar in spirit. Please note it. All these things, please make sure that one doesn't make a transcription error, since there are various symbols hanging around. Okay. Yeah, so that's what we have done. We have used that P1 plus P2 plus P3 equal to 1. I think it will be a good practice to take down notes as you are attending the class, because writing down something once is equivalent to going over it quite a few times. So now to find the probability M1 equal to K1, M2 equal to K2, you have got the expression this here, and you have to sum this expression with K3 running from 0 to infinity. But when you sum the expression the K3 0 to infinity, the first two things are not affected. You will only be summing up this last one, K3 to infinity. I mean, K3 equal to 0 to infinity. But that is all the possible values that the Poisson random variable with parameter this can take 0 to infinity, all the integers. So if you sum that out, it is 1. So you have that probability probability M1 equal to K1 and M2 equal to K2 is precisely just the first two terms, because the third term, when you sum over K3, it becomes 1. So this gives us that M1 and M2 are independent with appropriate Poisson distribution. And of course, this P1, since we have also found P1 and P2 earlier in the day, P1 is this, P2 is. Plugging that in, you get this parameter is here, this and this one. that shows M1 and M2 are independent Poisson random variables. So this shows that the process MT has independent increments, right? Yeah. So MT is the number of customers who have been served during 0 to T. So if you take two disjoint intervals T1, T2 and T3, T4, the people who finish their service between T1 and T2 are precisely your M1, that is type 1 people, and those who finish between T3 and T4 are that is the type 2 people, that is M2. So now that we have shown that these are independent random variables, consequently, the process has independent increments. And the second requirement was that the increments should have the appropriate Poisson distribution. And that's what we have found now. So you now know what the intensity function or the rate function for this Poisson, non-homogeneous Poisson. So the intensity function plays the role of that constant lambda in the case of that homogeneous process which we saw. That role is being played here by this function. Here the function is lambda times gt. So this lambda comes from that Poisson process n, homogeneous Poisson process nt, which governs the arrival rate, the arrivals. And the service time is a function. It's not a constant. So if the service time happens to be a constant, then you are back in the situation of homogeneous process. So to get this kind of conclusions, the important role is played by the that connection between homogeneous Poisson process and the order statistics of uniformly distributed random. So that many of the computations are reduced to playing around with the uniform distribution, which is generally easy to handle. The uniform distribution, the exponential distribution, the Poisson distribution, the binomial distribution, and of course also the normal distribution. These occur in many places because these kind of probability density functions are mathematically amenable. So in any kind of situation, one tries to see if certain kinds of assumption can be made so that the problems are reduced to handling such distributions. And how these kind of assumptions are realistic, that of course by practice, and it also turns out that many of these things are fairly realistic. So that is because many of these things are, the nature seems to be favoring these distributions. See, we saw the deriving the Poisson process, we did not make any very strong assumptions. All seem to be fairly reasonable assumptions. And ultimately, the net result was a counting process which satisfies these assumptions is only the Poisson process. And similarly, the geometric distribution, exponential distributions, all these things arise out of these objects, coin tossing or Poisson process. And of course, in another kind of setup, the normal distribution, and so on. Central limit theorem is also a similar result. You assume very few things, but then the final result is a very powerful result. So that is why you see normal distribution playing role in many contexts. Those of you who may be doing partial differential equations might see it in the context of heat equation or diffusion equation. Okay. Yeah. So that finishes that example. So now you take the example 2 of Poisson process 3. That is that radioactive thing. So combine that argument, and along with the argument which we have done here in this example. So then, plus of course, some more work is needed. The Poisson process of example 2, I mean the example 2 of Poisson process 3, or there should be 3 here, are actually independent non-homogeneous processes. In the argument given here, we had shown that for a fixed T, this should be N1T. So that's a typo here. N1T. Please correct it. We had shown for a fixed T, N1T and N2T are independent random variables for any fixed T. And also we had found the distribution of that to be a Poisson distribution. So some more work basically to show that, for example, if you take N1S and N2T, different S and T, that kind of things, they are also independent random variables. But that involves, the main step was showing that N1T and N2T for a fixed T are independent. That has been achieved. So now if S and T are given, S is less than T, let us say, then you have the random variable N1S, N2S, then N1T minus N1T minus N1S. That is what is happening between S and T, and similarly the corresponding thing. So for a fixed S, these two guys are independent. For fixed T and S, the second guys are independent. And also you know that N1T as well as N2T for the larger things are also independent. From this information, you can get that N1S and N2S. N1S and N2T are also independent. That involves some work. Plus extending it to any finite random variables. So the N1 and N2, those processes which we had seen in that example, are actually independent non-homogeneous Poisson processes. So many of the non-homogeneous Poisson processes you might see very often arise from something which involves the homogeneous Poisson process as a kind of starting point, as we had seen in this queuing theory example, where the arrival of the customers are governed by homogeneous Poisson process, whereas the output thing is a non-homogeneous Poisson process. So in the problem set also you will be given some exercise that is non-homogeneous Poisson process under certain conditions. You can convert it to Poisson process, homogeneous process by some time change. So the next result is in the similar direction, but it is simpler to prove because the next result will involve only homogeneous process. We will not prove it here. Yeah, please note it down if you want to. So let k be an integer and pi with I varying from 1 to k be numbers between 0 and 1 such that they add up to 1. So let nt be a time homogeneous Poisson process with arrival rate lambda. Now, next thing is, supposing in this situation, each arrival we can allot a type to that arrival which is independent of the time of arrivals and so on. Suppose any arrival is classified as type I with the probability pi. This does not depend on the time of arrival. That is, that the time at which they arrive do not determine the type. For example, if a new customer is a female or a male, that is independent of the arrival time. Things like that. Or nowadays, we may say that some person who is coming for some service is a senior citizen or not, or super senior citizen, or senior citizen, or able-bodied person, and so on. So now you can more or less guess what is going to come. Let NIT be the number of type 1 arrivals during 0 to t. For I running from 1 to k. Then the conclusion is these NIs, these processes are independent, they are independent processes, time homogeneous Poisson process with arrival rates P1 times lambda, P2 times lambda, Pk times lambda. Of course, the converse, you know, if NIs are independent homogeneous processes, their sum. Remember that N1 plus N2 plus Nk is N. If the components NIs are independent processes, then the sum is also a Poisson process. This we won't prove. In light of what we have done so far, these things can be done. So we will not spend time on. So next we will consider that, I think we will consider the next class. That is just, by the way, this kind of process is also called marked Poisson process in some books. That is the type as well as these NIs together that will constitute the marked Poisson. Anyway, we will not necessarily introduce terminology. Yeah. So next, this thing we will look at just one example of Poisson process with the random intensities. So xt, let's say it is a counting process. That is, let's say x0 is 0, and each xt is a integer, non-negative integer valued randomly. And in addition, suppose that if the parameter is given to be lambda, then xt plus s minus xs has a Poisson distribution with parameter lambda s. However, this parameter itself varies according to a random variable, capital lambda. And capital lambda is a random variable taking value in 0 to infinity. So that is, it is a counting process depending on a parameter which itself is a random variable. Such a process is called a Poisson process with random intensity. So conditional on capital lambda equal to lambda, xt is a time homogeneous Poisson process with arrival rate, lambda. So next class we will look at one example where this lambda is governed by an exponential distribution. So we will stop here for the day. If you want me to go back to any of the slides, I can do that. Okay, let me stop sharing. Again, only the usual two are around. The midterm exam, I plan to have it on Wednesday, the 16th of March. So let us say between 10:30 and 12:30. So I will send a notice to that effect soon. So probably today itself I will try to send. Okay, we will meet on Friday.
Thank you, sir.
Thank you very much and take care.
Thank you, sir.
You're welcome.